And you are of course most welcome. This is Project Euler problem number 4. A palindromic number reads the same both ways. The largest palindrome made from the product of two two-digit numbers is 9009. Find the largest palindrome made from the product of two three-digit numbers. Okay, so the brute force solution is very ugly and very slow, but pretty obvious. So we'll cycle through every possible pair of three-digit numbers, find the product, see if it's palindromic, and then see if it's the biggest palindrome. So 100, and we'll multiply that by every other three-digit number from 100 to 999, and eventually we'll get down to 999, multiply that by every three-digit number. So something like 880,000 iterations there. So it's going to take a couple of seconds, I think. Biggest equals 0, and then we'll have a nested loop for the three-digit numbers for I in range 100 up to 999, and Python's weird, so I have to put 1000, and then for j in range. And now for this one we can put I plus 1, because 100 times 101 is exactly the same as 101 times 100. So we don't need to do that calculation twice. So this might save a few iterations. So yeah, that makes sense. Okay. So what are we going to do now? Oh yes. So we're going to turn our integer into a palindrome. So take the product, I times j, turn the integer into a string, and then reverse it. So if string p is the same as string p reversed, which in Python is just a matter of doing colon colon minus 1. So we've established whether the product is a palindrome. Now we need to establish if it's the biggest palindrome. So and p is bigger than biggest, then biggest equals p, and that is pretty much it. Biggest. There we go. Right, I actually want to see how long this takes, so I'm going to break with tradition and get rid of the browser so you can see the output. Now this will allow you to see the answer to the solution, but if you copy the code you'll get the answer anyway, so it hardly matters. So I need to import time for this. From time, import time. So we're going to set the watch going here. So start equals time. And then down here we're essentially going to take a lap time. So how does it go now? It's time minus s, time minus start. There we go. So that there sets the clock going, and that there stops the clock and tells you how much time has elapsed. Hopefully the code works. Yep, and that was about half a second, so 500 milliseconds. Pretty slow. There is a much quicker way of doing this. So the problem with this algorithm, apart from the fact that it's brute force, is that it's going through every possible combination of two-digit numbers and then checking if the product is a palindrome. Well, why don't we just generate all the palindromes right at the start? So let's say we start with 999. Next door's dog is just having a psycho fit, so sorry if you can hear that. Does that from time to time. Anyway, I think it's actually attacking somebody. Oh, anyway, let's say we start with 999, and then we get the reverse of 999, which is 999, and then stick them together. then you get one palindromic number. Or better example, start with 921, turn it into a string, as we've done here. So we turn it into a string, then we reverse the string, and we stick the original and the reverse together so we concatenate them, and then we turn it back into an integer. So yeah, that I think is going to be the best way to do this. And then we find a nice neat algorithm to find out whether that 6-digit number has a pair of factors that are both 3 digits. Whew, okay, right, so we start with n equals 999. Then, right, we're going to need a while loop, I think. Found equals false, and then while not found. I don't even need that, it's while true, isn't it? I'll just do while true. While true. And then, right, so now we need the current palindromic number. So current equals string n plus the reverse of string n. And that generates a palindrome. Then we're going to convert all this back into an integer. So int and all this. There we go. If, so I'm going to write the so I'm going to write a function that finds all the factors of the current number. So I'm going to do that separately. So has 2 factors current. So if the current number has 2 factors or a factor pair that are both 3 digits, then we have found the answer. So print current, and then we can break out the loop. If the current number is not the solution, then we have to decrement n, so n minus equals 1. Right, now let's write this function here, so that can go here. Def has 2 factors. Let's move this down, we don't need to see this ugly old algorithm. So we'll start with n, so n is being fed in. Right, so how is this actually going to work? Let's scale it down slightly. Let's say I've got a 3-digit number, 110, and I want to know if it's got 2 2-digit factors. So let's take the square root of our big number, and then we're going to round it down to the nearest integer. That will give us 10. Now, does 10 go into 110? Yes, it does. It goes in 11 times. So we have found a pair of factors that are both 2 digits. So that's roughly the algorithm we're going to use. Excuse me a second. Okay, so let's take the square root of the big number, so we'll start there. F equals the floor of the square root of n. So I'll have to import floor and square root from math, so from math import floor and square root. There we go. And the next thing to do is what are we doing next? Oh, we're going to break into a sort of while loop, aren't we? So while, so f is going to start at the square root of n, but it can't go any lower than 100. So while f is greater than 99, so f is the first factor, and we're going to use it to find the second factor. So while f is greater than 99, so if n divides equally by f. Now, okay, so if n is a factor of f, if f is a factor of n, we can guarantee by this while loop that f will be 3 digits. We then need to know if the other part of the factor pair is also greater than 3 digits. So, and n divide by f in range 100 to 1000. I think that's probably the best way to do this. And then, so if it satisfies both of these conditions, we know that our number n has two 3-digit factors in a pair. So return true. So if we get to this point, then we can actually return true and we don't have to do anything else. So if it's not a factor pair that we're looking for, then we have to decrement f, and if we get right to the bottom, we have to return false. Right, I think that is going to do it. So right, let's take a timestamp for this as well. So we'll go mid equals time, and then once we spit out an answer here, we'll do time minus mid. So let's compare the two algorithms and see which one is the quickest. I'm hoping that this one here will be a fair bit quicker. So let's see. Yes, you see, so that's half a second, and that is 2/100ths of a second. So that's 50 times. I don't know. It's a lot faster anyway. So yeah, that's going to be it for this week. I will not be doing problem 5 because I did not solve it programmatically. I just did it using pen and paper, so I won't discuss that one. We'll go on to problem number 6. So see you then.